Hello, welcome to Speed Reducers, the fundamental element of robot performance. I'm Jack Schorsch, the CEO and founder of IM Systems. This talk is recorded for IROS 2021, Prague, Czech Republic, specifically for the workshop From Gears to Direct Drive, Recent Trends and Opportunities in Actuation. In the first version of this talk, I was drilling quite specifically into the selection and usage of speed reducers and the implied limitations on robotic performance. But after going through and really walking through my talk and seeing what I was discussing and looking at the other speakers and topics, I've made a bit of a shift in focus. For that change in direction, I do apologize. If you want to grill me in the open discussion, please feel free to do so. I really do enjoy talking about those details. But I think my other colleagues on the panel and in the room actually can do a very good job of describing the various technical performance limitations of speed reducers and the implications for that in robot systems. Because of my experience in industry, especially in trying to see new technologies get adopted, I've actually decided to choose to focus on a bit more of a pragmatic topic. With all of this very interesting research being done at universities and corporations around the world, why are these technologies failing to find adoption, both at a system architecture level, but in a wider real-world deployment scale? The industry is littered with promising technologies in robots. Shaft robotics, Rethink robots, even Boston Dynamics has been bought and sold how many times? And they're probably the most compelling, most interesting robots that the vast majority of people have ever seen. Now, these things are scientifically fascinating, incredibly useful to the robotics community, but they're being relegated to backwater or niche cases, or they're dying altogether and being salvaged out of bankruptcy, out of sort of particular passion products. And today, I want to dig in a little bit more into what I see the proximate cause of this, especially from the viewpoint of a robot component developer. So a little bit about me and my background. I've been working in R&D for 21 years now, and notably have overlapped both Dr. Roos and Dr. Sensinger for several years after John finished his PhD and Elliot was working on his. This is while we were both at the Rehabilitation Institute in Chicago. They are both presenting in this workshop as well, so it's quite nice to be here with them as well. Mike first started working with developing test setups and devices for use in the physiology department at Loyola University Medical Center in Chicago. There, I was mostly working one-on-one with the individual researchers to build novel test machines to test particular research hypotheses. And that was where really I had my introduction to what the research community really cared about. Typically, of course, researchers are looking for some answer to a question that was stimulating to them. Of course, they place this in the greater context of the field, but it's really these things, these building blocks that really motivate them to be fascinated and work on a problem. These questions are how, why, where, what kind, these really basic scientific questions, and I was supporting them there. After Loyola, I went to study medical device design in Los Angeles under Jerry Loeb. I took that back to Chicago to work for Dr. Richard Weir and Dr. Todd Kuiken at the Center for Bionic Medicine at the Rehabilitation Institute, again with Elliot and John, where I was tasked with getting a microimplant through animal testing and into human trials. While I was there, though, I had a chance to see something that I think is actually fairly rare in academic research, and that is the people directly affected by the research were in close daily contact with scientists. So RIC is a working, excellent rehabilitation hospital, and it is a first-class researcher of advanced rehab techniques and technologies. So you have on both sides, you sort of have the people you're affecting directly, but also the key academic work being done in the same place. So observing this, especially the quite often vast gap between technologies that were good enough for lab and scientific studies to good enough to be useful in the field, was really a foundational experience for me. After Chicago, I left to work on my PhD at the Delft University of Technology in the Netherlands, specifically in wearable robotic systems, exoskeletons, and things like this, under Dr. Frans van der Helm and David Abink. While I was there, though, I met the downfall to what should have been a really nice research career, and that is our group was waiting for a test exoskeleton to be fabricated, moving a bit slower than we expected, so pretty typical for hardware building and academics. So I submitted a small proposal to study a new idea for a gearbox, something I've been working on and off for maybe a decade. It got funded, the math worked out, I did a preliminary pitch to the industry and saw that it was really quite interesting. So I left the university to pursue building this gearbox full-time and have been working on it ever since. This brings me, of course, to the startup. Describing a little bit about it and understand what we do and my background for presuming to lecture all the very smart people in this room or their living rooms about what they need to do to make improvements in the adoption rate and acceptance of new technologies. So the company is IM Systems. We make something called the Archimedes drive, which to be more properly described is a compound epicyclic traction-based speed reducer. In a very simplified explanation, we make a toothless Wolfram-type transmission so as to avoid the problem with tooth mesh and recirculating power that those systems typically suffer. We're at 10 FTE with a pair of supported researchers, one at Delft and one at Twente. We've been in business for 5 years now. We've spent somewhere in the neighborhood of 6 million euros on translational research, specifically making the drive good enough to be somewhat useful in the real world. Perhaps 15% of that total technical budget is directed towards theoretical research, with the rest going to such mundane things like lifetime testing, grease and lubrication evaluations, materials testing. So the stuff that typically tends to get very little attention when you're writing a paper, but gets a lot of attention when you are trying to integrate a mechanical component into system architecture. Before we move any further into this talk, I should address my bias and my personal position because, as I've mentioned, I am not working for a university. I'm working for a startup, and I'm sort of directly financially, I have a vested interest in how this conversation plays out in public and in the research community. So we design and make compact speed reducers specifically for the robotics market. I've tried my best to not provide a point of view only from this perspective, but it is in the interest of disclosure that I want to make this very explicit, that I do have a degree of financial interest in this presentation and also in my viewpoint. So please take everything I say with a fair grain of salt. So this is a slide which is taken directly out of our startup's problem statement, less the comment about bias. So robotic systems in industry are fairly remarkable in that their architecture and base mechanisms have been pretty static for decades now. You've got your servo motor mated to a cycloid strain wave planetary gear set, some large bearings, cast structural housing. Maybe in the case of a cobot, you're going to have a force sensor and an extra encoder in there, but really a robotics engineer from 30 or 40 years ago, you could open up one of these robots and he would be completely at home. But it's quite interesting to note that in every conversation I have with industry, there's this message that they would really like to move to better mechanical hardware, but from their perspective, better drives don't exist. Yet we go back and we look at the research and there's better stuff technically being invented all the time, being discussed, being reviewed, being proposed. And I want to get after that question. I want to try to understand, where does this come from? What's going on? Why is there perception gap exist between what the academy, universities think and what the industry thinks? So I like this slide. This is really, it's a favorite of mine, and it's a favorite of mine because it's timeless. You could have found this in a news article from the year 2000, or it could have been from a news article from literally yesterday. And what that points at is that even though the world and everyone seems to think that robotics are really this cuspal technology to just explode out into the wider world, that's been perceived to be happening, to be just around the corner for a very long time. And there's always this caveat: if a few things can happen first. It's implied that it's a few very simple things, but I would argue that actually the vast majority of work still needs to be done before you can realize a promise like this. Now we're getting into a bit the meat of my talk, and this is, where do things go wrong in meshing the academic research with wider adoption of all these great technologies we invent? So I've come up with a very simple hierarchy of common robotic literature. This is my quite somewhat subjective view of things, and it is that there are sort of these four nested concepts and categories of papers. You've got way down at the bottom, it's the design of new things, and not just new systems, but really new widgets. You've got new motors, new gearboxes, new sensors, new batteries, new power systems, really all the physical new architecture. And this is an extremely popular topic. It feels like a very compelling topic, so it feels very interesting from a research perspective, and it's very supported by the industry. The industry always says, we would love to see these things. Robot developers say, oh, we would love to have these features. Going up from new mechanisms, etc., is new system architectures. This is different ways of combining all of their subcomponents into new useful robots. So these are things like the first cobots. That was a new system architecture. You put force sensing or you put extra encoders into these joints, and all of a sudden you had an architecture that was quite useful for a lot of new tasks. We've built whole new categories of robotics based on these things. Above this, you've got task planning, path planning, control schemes. These are techniques and technologies to take advantage of existing system architectures and get more out of it. So really to figure out, what are the optimum ways to do navigation inside of a warehouse? What's the best way to do motion planning, especially in a flexible environment? What's the most efficient control scheme? How do you make it stable? And then finally, kind of wrapped all the way around it, is techniques for figuring out the analysis of performance. So how do you judge the performance of your robotic system? And these are my major categories, and there are many subcategories, and you may disagree somehow how I've placed this architecture, but this is my view of the way the research world works. This helps us to refine our understanding of the problem. When we understand that this entire, and maybe even more layers, need to be considered when you're looking at industrial adoption, this layer cake of problems has to be addressed before you can truly say you've completed development. And it becomes clear that we're all looking at a far more complex problem than it appears. So each layer of novelty is going to confound the others as they're interrelated. So new mechanisms are going to affect the design of your system architecture. If you have a different gearbox, it's going to affect the system architecture that you choose. The choice of your task planning and your control scheme are then dependent on that system architecture. And in turn, that's going to affect your performance analysis. That leads back to the original problem. Why, when a new mechanism research is so popular, are such mechanisms so rarely adopted for future system architectures? And this brings us back to a practical, real-world limitation. So resources, typically time and money, are limited. Academic grants are often structured around your typical PhD process. If you look, there's a remarkable synchronization. You've got 4 to 5 years of development, results in a discrete and useful piece of work. But when faced with this time frame, because of this dependency factor I'm talking about, even if a novel mechanism, motor, sensor, seems to be ideal based on published work, it's rarely going to be chosen as the platform to build a new system architecture around. And that just gets back to the time issue. If you've got a completely new technology that somebody else has invented and you're trying to integrate it, it's going to be very, very hard to do so because you don't have the experience, your lab doesn't have the experience working with it. This brings us to our real problem, that any killer issues which show up in your dependencies, they're going to prevent you from addressing your bigger questions. Remember, none of this stuff is easy. Making a new robot architecture is a significant understanding. And unless the new physical hardware is truly enabling, adding it to your project just exposes you to a clear risk of failure versus a marginal improvement in performance. So this rarely happens. Not only are introducing the risk of failure into your project, but if your physical components don't work out right, that of course is going to just be an immediate fail. But often these new subsystems and new components are lacking in key characterizations that are going to prevent you from designing in parallel. Things like your friction model, clogging torques, bending stiffness, sensor robustness. These are all things that are exceptionally hard to predict accurately enough during the design process. They are critical to the design of your system architecture and your control system, but are also fairly simple to measure experimentally. So there's a lot of bias here against about using that, and it implies a significant time lag for a new system. If you don't have that test specimen in hand on day one, you're going to need to work on your system architecture without that knowledge. And if it turns out that there's a difference in between what was predicted versus what obtains in the real world, you're going to be faced with a choice to accept a suboptimal solution or go back and redesign the architecture. And we've all been there, right? Go out, you pick a beautiful piece of technology, you decide to use it, and it does not quite work the way you thought it did, and then you are left scrambling. You have to pick a new motor driver, you have to pick a new sensor, you have to redesign the housing to accommodate these new things. And because you made a choice for new hardware, you redesign your architecture again and again and again. And that is very expensive in terms of both time, but also money. It's not just in research projects that this happens, it's industry as well. I've been working in an industrial startup out of the academy for a long time, had the chance to discuss actuation, drive technology with virtually every major company out there, and I found something really remarkable, is that basically every robot maker develops dissatisfaction with the state of the speed reducer market, so my space. They tell us they would love better drives, lighter drives, more accurate drives, cheaper drives, all this great stuff about that we see out there in the academic literature, but when the rubber meets the road, every manufacturer is still using literally exactly the same drive mix that they were using since before most of us started our careers. Every maker, excluding the resurrected Rethink, is still basing their mechanical architecture around cycloids, strain waves, planetary, spur gears, maybe some direct drives. Now, the youngest of those is almost a century old, and it sort of begs the question, why do they do this? There's two contradiction priorities. They express this priority of we would like better drives, we'd like just, great hardware, and they go back to the tried and true standby. And I would argue that it's because they've not really quantified what better means. And better doesn't mean just technically better. It means technically better and industrially relevant. So it's robust. It is well characterized. Perhaps this dichotomy is most visible if you do a simple search through the news, in the journals, via Google. You'll be really encouraged by the breadth and volume of work that's being done in the space of new actuation for robotic systems. If anybody in this room, if your paper is cited here, it is not directed at any individual. These are all fantastic pieces of work. They're very interesting, but It becomes a cautionary tale when you look at some of the giant work in the space. You look at Gil Pratt's papers on SEAs, and they're actually old enough to run for president. I was a freshman in high school when those papers were written, and I believe the only commercial robots who have tried to use series elastic actuators, so like really widespread deployment, that would be Rethink. And other than that, they've been really adopted inside the industry. And the reason for that is it's taken essentially a generation to train enough people up, enough researchers, enough research groups to fundamentally understand what's going on with SEAs to be able to use them now in their system architecture. So it's taken a generation to make this a common core mechanism that's no longer so risky for your architecture. So the biggest de novo drive system of the last half century were cobots. They went from nothing to something. Colgate and Peshkin's patents, 20 years old now, but even there, within a new class of robots, the same mechanical systems prevail. So Universal, the largest cobot maker, uses exclusively strain wave gearing. And other large OEMs with cobots tend to build them on architecture shared with their industrial robots. So if any product was well positioned to take advantage of new drive technology, it would have been cobots. No preconceived notions. But this didn't happen, and it's why. Why doesn't this happen? To understand why people are choosing the existing architectures over time, it comes to this, and it is that the existing technologies are well understood. Researchers, industry understands the benefits of these systems and how to work with them. They can look up data sheets, they can look up performance tables. You've got your planetaries and spur gears. You know they're going to have good efficiency. They're going to have relatively poor backlash characteristics. They're going to have relatively poor torque densities, but they're going to be quite affordable to manufacture. You know this. If you have questions, the manufacturers are very well established. You can get their data sheets, and you can modify them basically to be exactly what you would like them to be within the space that they operate. And it continues on for the other drive technologies. You've got your strain waves and harmonics. These have been around for the better part of a century. They're well understood. The friction models are well available. There's a vast quantity of research discussing ways of optimizing these drives, of improving upon their performance, in finding niches and using them in robotic applications. Cycloids, it's the same story as harmonics. If you're looking for something with a high stiffness, a reasonable accuracy, reasonable cost, and very good load carrying capacity, that information is available and you can buy this off the shelf. And then with direct drives, they're not so popular for robotics simply because the amount of copper you need to typically perform most robotic tasks is high. But they are getting better, and they're very well understood, being essentially large servo motors. So the key feature across all of these is that they are widely available. You can buy them immediately, start evaluating them for performance, figure out how to integrate them. And if you've got questions, they're backed by very large organizations where you can get the data sheets and the information you need to improve on your system architecture. So basically, people choose these kind of drive technologies and these kind of actuators because they are, frankly, easily available. It is a time and money decision. And I believe that this will remain the paradigm. They're widely available, they're of commercial quality, and in this instance, commercial quality is something that is actually quite a good thing. It's that you can buy it off the shelf, it'll work, it will behave the same as all the other models that you've ever purchased. The technical performance is reasonable. Maybe it's not ideal, maybe it's not perfect, but it's reasonable to start from and can very often be expanded for your niche use. And I think mostly one of the key things here is there's a deep, relatively easy access to the broader knowledge base around the technologies. So experimentation and understanding of a cycloid drive can be performed by really any of us in this room. You can buy a cycloid drive from Neptesco, and you can put it into a dyno, and you can test it, and you can understand fundamentally what's going on inside of that drive. And that means that if you want to make modifications or improvements, it's quite easy for you to do so. With a new technology, you've got to come up with all that knowledge base yourself. So a very bright researcher publishes an academic paper, sends it to ICRA, I don't know, 5 years ago, about a very interesting compound traction drive, and none of that meat is there. None of the tables about the friction characteristics, the Strebeck curves, the Coulomb friction, nothing about the seals, nothing about the longevity. None of that data exists. And I would argue that it's that secondary information, sort of the easy stuff, from a technical perspective, it feels easy, is what hampers adoption. If you don't know how it's going to work, you can't adopt it. But in the academics field, we often very rarely focus on this kind of behavior. I honestly can't think of a research project that has done testing like we've done inside of our lab, inside of our company, to validate out some of the more boring aspects, but kind of essential to adoption aspects of drive technology, like what does the friction look like 2 years, 3 years into adoption? How does it wear? How does the oil stand up? These are not interesting questions from really a pure academic perspective, but they are essential questions from an adoption perspective. And I would argue that that really creates a barrier and a bar to adoption. So if we don't fix this, if we don't address this, we're going to be lagging further and further behind. And we're going to see a lot of good ideas essentially get through the PhD and postdoc stage and then wither on the vine or maybe turn into a very narrow niche project. This brings us to our approach a little bit. What we see as valuable and what we've seen also the industry pushing us at is that even after we've done our technological proofs, showing the drive can lift heavy weights, can move with high accuracy, can do sort of all the interesting and relatively straightforward measurements to complete, we had to go back and start validating everything. Start building the control models, start building the friction models, start doing life cycle testing. And this kind of work, the professionalization of a new technology, is very often left out of the academy and even the innovation groups within corporations. And it tends to be trivialized, at least in my opinion, by many researchers as pedestrian or simplistic or really not academically worthy. But the amount of money which is spent inside of large corporations to make a product out of a new invention really belies that trivialization. It's incredibly expensive to take a new invention and make something that works really well and really robustly. It is not a trivial process at all, and I think we should, as a community, really validate that and really reward efforts in this direction. So taking a technology from it works really good in my lab under these circumstances to you can just take it out of a box and plug it in and it works is a project of scope equal to any academic project that I have ever seen. And that should be recognized and that should be encouraged and that should be actually incorporated in at a really fundamental level to basically everything we're doing. And this lack of professionalization of things we build is, in my view, a hindrance to the field. I'm happy to apportion blame in the matter of this to the developers of new mechanisms, rather than the system architects. I sort of feel like taking on this blame is a bit okay, since I view myself as a mechanism builder. I'm a tinkerer or a toy maker. If the developer of that piece of hardware doesn't know how to, or care enough to bring a technology up to a usable state for someone else, why would a researcher pick that challenge up for themselves? So it's really something that's kind of on us as mechanism builders to make this easier for people to adopt it. When I say professionalization, what I mean is this. And this is a plot of the life cycle of various generations of my drive. Essentially how close we are able to reach the real operational target life. And you can see in June of 2017, we actually had prototypes up and running that were pretty good. You know, from a technical perspective, they had very nice torque, they were very accurate. And you can see they melted at about 0.6% or 0.06% of operational life. So that means that they were totally useless for anybody who wanted to try to build something with our drives. We're talking hundreds of hours tops. And we decided that this had to be better because nobody's going to take that risk in evaluating it. Nobody's going to try to use it. We had to do more. So we started working on life cycle refinements. We started doing a lot of research, did a lot of academic research, and we started building prototypes. So each one of these prototypes that you see on the little chart represents a significant design effort. You can tell that basically by the year to, the 6-month gaps to a year gap between prototypes. That is a year of the full involvement of a team of half a dozen people. That's the effort to bring one layer higher in the lifecycle forecast. And it's really important to do this sort of stuff because a year later, or a year and a half later, we were up to almost 0.5% of life. So we've gone, we've order of magnitude improvement, but still not useful. 6 months later, though, with the next generation, we were becoming useful. And then finally we kind of hit our stride and we're able to achieve really operational life. But this is a 4 to 5 year process to bring that to fruition. And until we completed that, our drive was not particularly useful for anybody. And I would argue that these sort of tests, to at least get it to, that 1%, 2%, 5% usable life are what you have to do in order to get a technology adopted. So this may have been a bit of a winding talk. It may not have finished on a super optimistic note, but I think and I hope that I've brought to you my perspective on what's going on with hardware adoption in the field and what we need to do as a community to really see our hardware be adopted and really make more contributions to the field. In short, in conclusion, I would say that new hardware, it is adopted because of its technical capabilities, but it is not adopted because of lack of robust data sheets and testing. Those two things can both be true. People pick something for the benefits, but they refuse to use it because they have fear over the unknown, and they don't want to spend all their time and all their effort on something they're unsure about. I believe that research projects at academic institutions should invest a lot more effort into the professionalization of their solutions. I think every research grant that has a build something component should almost mandate the testing and publication of user data or operational data for those systems, simply so that the next group who wants to pick it up has a better basis to work from. And finally, I also think that validation and verification testing should be considered really academically valid and even an essential component of a research project. I know if I was reviewing a hardware project, something that had a hardware component into it, and it didn't consider the usability of that hardware in the bigger scheme of things, I'd find that proposal very unserious. Now that I've spent so much of my career in trying to bring these technologies from lab to table. I hope you're interested in this talk. I hope you've enjoyed spending the, looks like half an hour now listening to me. Thank you for listening, and I look forward to your questions and the discussion during the live session. Thank you.